Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends, to your younger brothers and sisters who would want to take up engineering in the future, and to your relatives. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Hello, future engineers. Here is another video in structural analysis, particularly in computing deflections, this time by area moment method. If you want to anticipate the solution to this problem, you may do so by pausing the video. So by area moment method, determine theta A and delta A. E is 200 gigapascals and the moment of inertia is 450 times 10 to the 6 mm to the fourth for the portion where it is labeled I here, and this is 2I. So first, let's compute the vertical reaction here, which is obviously downward, so that its moment about C is clockwise and counteracted by the moment of the 45 kilonewton load, which is clockwise. So 45 times 3 equals downward reaction at D times 3, cancel 3, so this is also 45 kilonewtons downward. So the moment diagram by parts centered at C would look as shown in the figure. So 45 times 3, 45 times 3, that would be 135, but because as it enters this portion, the moment of inertia is 2I, so we divide by 2. 45 times 1.5 is 67.5. Then divided by 2, so 33.75 here. Then 45 times 3 is 135 supposedly, divided by 2, so 67.5 as shown. So this is the area which is symmetric with respect to C, and therefore if we divide this trapezoid into two triangles as shown, so EI division of A relative to C, because we have the same area and we sum up moments about A, that would also be division of E relative to C, because we have the same area and the moment arms of area or distance of centroids of individual areas from E is the same as the distance of the individual areas of the left portion from A. So that's also EI division of E relative to C. And let's just focus here. It is equal to this area here, 1/2 of 1.5 times negative 67.5 times 1, where 1 is 2/3 of 1.5, so this is 2/3 of 1.51. Then plus this area here, 1/2 of 1.5 times negative 33.75. 1/3 of 1.5 is 0.5 plus 1.5, so the moment arm is 2 from point A. So plus 1/2 of 1.5 times negative 33.75 times 2. Then lastly, for this area here, 1/2 of 1.5 times negative 67.5, moment arm is 2.5, where 2.5 is 2/3 of 1.51 plus 1.5, so 2.5. Simplifying, EI division of A relative to C equals EI division of E relative to C, and that is equal to negative 3645 over 16. Negative means the tangent from, that means that A is below the tangent at C. E is also below the tangent at C. As shown in the figure, if that's the tangent, then point A should be here. E is there because that's a support. So this is division of E relative to C. This is division of A relative to the tangent at C. So below, the point at A is below the reference tangent at C. point E is below the reference tangent at C because the value is negative. So as shown, this is deviation of A relative to C, deviation of E relative to C. But the tangent at C is inclined up to the right, so this is positive. Or from the horizontal to the tangent at C, we have counterclockwise rotation, and counterclockwise rotation is positive. Or you just look at the tangent, it is indeed positive. So that's theta C, which is positive from horizontal to the tangent counterclockwise, so that's positive. And it is opposite over adjacent. So we just make division of E relative to C positive, then divided by 3. So theta C is equal to 3645 over 16 over 3, then over EI. So that's why it is equal to 1215 over 16 EI. That's theta C. So this value here, tangent of theta C is opposite over 3. So this is 3 times theta C, that value there. And since this is a point on the elastic curve A, the deflection at A is negative, and it is negative of the quantity 3 theta C plus deviation of A relative to C treated as absolute value. So that's delta A. So basically it's negative, A is here, and it is the negative of the absolute values of these two values here. So we need to solve deviation of A relative to C. So delta A is negative of 3 times theta C, which is 1215 over 16 EI, then deviation of A relative to C, which is 3645 over 16 treated as positive because the sign is here. So delta A is equal to negative 455.625 over EI. But since E times I is 200 gigapascals times I 450 times 10 to the 6 mm to the fourth, 200 times 10 to the 6 kilopascals, kilonewton per meter squared, then times 450 times 10 to the 6 divided by 1000 to the fourth to convert this to meter to the fourth. Then that would be 90,000 kilonewton meter square. So we just divide this by 90. That's the shortcut to make it mm automatic. So the numerator is kilonewton meter cube divided by 90,000 kilonewton meter square. So meter originally. So we multiply further by 1000 to make it mm. So that's why we just divide it by 90 so that this value is in mm automatically. So delta A is equal to negative 5.0625 mm. Having found delta A, we then compute EI theta AC, the angle between the tangents at A and C, simply the area between A and C. So EI theta AC is, we just copy these areas here, but I treat this area as trapezoid. So 1/2 of 1.5 times negative 67.5, then plus 1/2 of quantity negative 33.75, negative 67.5 times 1.5. So AI theta AC is equal to negative 2025 over 16. The magnitude of theta AC is greater than that of theta C, which is obviously seen here. And since it is negative, it means that from the tangent at A to the tangent at C, the rotation is clockwise. So theta AC is negative 126.5625 over EI in decimal. So this is the tangent at A. And from this tangent to the tangent at C, clockwise. So this is the horizontal. So this is theta AC clockwise, again from tangent at A to tangent at C, clockwise. So clockwise rotation is negative, that's theta AC. And it is less than theta A, of course, from the horizontal to the tangent at C, that's theta C, which is this. I just transfer the horizontal here. This is theta C, which is positive, so counterclockwise from the horizontal to the tangent at C, counterclockwise. So that's theta C. Therefore, from the horizontal to the tangent at A, which is this, counterclockwise. So obviously, the tangent at A is inclined up to the right, so that's positive slope. And to verify that from the horizontal line to the tangent at A, that's counterclockwise, so that's positive theta A. And obviously, theta A is the sum of the absolute values of theta AC and theta C, which is also equal to this, theta A from horizontal to the tangent at A counterclockwise. So theta A is theta AC positive quantity, theta AC plus theta C treated as positive. Everything is positive because theta is expected positive. So this is theta AC 25 over 16 over EI. This is the EI. Plus theta C, which is 1215 over 16 EI. So that's why it is 202.5 over EI. And since EI is 90,000 kilonewton meter square, 202.5 kilonewton meter square over 90,000 kilonewton meter square is 2.25 times 10 to the negative 3 radians. So there's no need to put the unit radian because that is understood radians. So that's it for this video.